something that we call the quark-gluon plasma, and I'm going to explain what that is in a bit. And I do this work at CERN, so the big laboratory in Switzerland, and I actually sit at Oak Ridge almost every day. I have also spent a lot of time at Brookhaven. The lines get a little blurry. There's a lot of people who work for universities who sit at national labs, and there's a lot of people who work at national labs who formally work at universities because it's easier to hire people. So what we do, we sometimes call it the Little Bang because it's a bit like the Big Bang. We're trying to study things that existed last shortly after the formation of the universe, except that we do this in the laboratory, so it's a lot smaller. And we're creating something called a quark-gluon plasma. So I'm going to start by explaining what a quark is. This is the standard model. This is my favorite representation of it because these little animals are roughly comparable to the scales between particles. So an up quark is represented by a duck. It's much lighter than the top quark, which is represented by a blue whale. So these are split into leptons. So you've got electrons. The electron's heavier cousin, the muon, and then the tau. And then there's neutrinos. On the first night, we heard a little bit about neutrinos. They're really, really light. And then you guys heard about, a little bit about photons. Photons are what we call the mediator of the electromagnetic force. There's also the weak force, and this is mediated by the W and the Z. But I'm going to focus on the strong force, and that's mediated by the gluon. And I'm also going to talk a lot about quarks. So these are the quarks. Normal nuclear matter is made up of up, down, and down quarks. And in the laboratory and also in high-energy collisions out in space, we can get charm, strange, bottom, and very occasionally top quarks. Top quarks are really hard to make. So these are what we start working with. So you guys are more familiar with the electromagnetic force. The electromagnetic force, if you have two charges bound by the electromagnetic force, as you pull them further apart, they get, the attraction between them gets weaker and weaker. And the strong force is the opposite. If you've got two objects bound by the strong force, when they're close together, the force isn't very strong, but as you pull them apart, it gets stronger and stronger. And this is a bit like a rubber band. So, one thing that we have that can be bound by the strong force is a quark-antiquark pair. And what happens if you try to pull these apart, at some point, it becomes energetically more favorable to just make another quark-antiquark pair rather than to pull them any further apart. So you try to pull apart quarks, you're never going to get them completely free from each other. You always see them bound with some other quarks. And this is a property called confinement. But, so what we see is that you get quarks bound in things called baryons, and you guys know two examples of this already. There's the neutron and the proton. And then we can get other baryons if we start adding these other exotic quarks. I'm a particular fan of the strange quark, so the lambda is one of my favorite baryons. We can also get these quark-antiquark pairs. Lightest is the pion. We make a lot of pions. And I like kaons because they have a strange quark, and I really like pies because they're very strange. And what we try to do is so we're never going to see these free quarks, but we're trying to see what we get when we have quarks that are almost free. So what we do instead is that we try to push them together. If we take nuclear matter and we push on it hard enough, we try to get to where the boundary between different hadrons is irrelevant. And this is what we're trying to form. It's called, and we call it the quark-gluon plasma. And there's a couple different ways we can do this. We could take nuclear matter and we could heat it up until it starts to melt, or we could take nuclear matter and we could compress it until the boundaries become irrelevant. And this is actually what we do in the laboratory. So this is what we do at the Large Hadron Collider. We take very high energy lead nuclei, and at this point, because of relativity, their length contracted, so they look really, really skinny. We collide them, we briefly form our quark gluon plasma, and then, as it expands, we form these hadrons, baryons and mesons. So an analogy is that if we went out in space and we collided two ice cubes, if we got them going really, really fast and we slammed two ice cubes together, we would melt the ice, we would briefly form water, and then as the system expanded, you would get little shards of ice, and this is our little shards of nuclear ice, which are hadrons, are actually what we observe in the detector. Now, it's a bad way to study water because we can actually melt water in the laboratory, but it's the only way that we have to study liquid nuclear matter. So, we do this. This is the Large Hadron Collider. It's been in the news a little bit lately, so you might have been reading about it. This is one of the places where we will do these types of experiments. There's another one called the Relativistic Heavy Ion Collider on Long Island, and that's where I did my thesis, so I have to give it a little bit of a plug. Everything about this is large. So there's there's two really large experiments. These are ATLAS and CMS. And these are, if you guys have read the newspaper articles and read about how there are searches for the Higgs, that's what these detectors are primarily designed to do. These collaborations have something like 5,000 people each in them. They're huge collaborations. So at one point, when my mom found out what I did, she said, "Oh, well, there's this guy at the University of Lincoln at Nebraska, and he's working on that too. Do you know him?" And no, there's about 10,000 people, Mom. And so these are huge. The experiment I'm on is called ELISE. There's 1,000 people there. I actually don't know all of my collaborators, but I know the people that I work with closely. There's another little experiment called LHCb, and I haven't put Totem on there and I haven't put up a picture of LHCf because they don't have a cool picture of their experiment that I could steal. But to give you a sense of scale, this is the SPS, the superproton synchrotron. This is what we use to speed stuff up before we inject it in the Large Hadron Collider. This has a diameter of 2.2 kilometers. And the big guy has a diameter of 8.6 kilometers. So, large scale. Here you can see the Geneva airport. This is located just outside of Geneva. And it is also located between the Alps and the Juras. And that means that there's a lot of good hiking. And I'm not a skier, but there's good skiing. These are pictures I took hiking with some of my collaborators. And this is an example of one of the large experiments. If you see any high energy talk, they will always show you a picture of the detector. So this is my detector. And it weighs 10,000 tons. Here for scale, you can see this is what a person standing next to it looks like. And so again, huge scales. These can be a little bit overwhelming at first when you see one of these pictures, because there's a lot of subsystems and they each